Very pleased to present you, if you don't know him already, Francesco Sette, who is Director General of the ESRF and who accepted to give you an introduction for the workshop. Thank you, Francesco.
Thank you, Marine. Thank you for being with us. It's a great pleasure to welcome you here at the ESRF. It's a great pleasure to share the excitement of the new restart of the ESRF machine in the coming months. And it is my pleasure to tell you a little bit what the ESRF is planning to do in the coming years and what has been working on over the last few years. You see the beauty, I refer to the beauty of synchrotron science, and here it doesn't want to change a view graph, so we really have a story here. Okay, that's good. So synchrotron science and X-ray science. So here, you know, we look at the spectacular success of X-ray science over the last century. And the use of X-rays in what I like to call the area of crystals has been so fundamental in understanding many fundamental issues that link structure, functions, and relations, and this has allowed us to understand materials and, in particular, crystals with large unit cells, protein crystallography, and so on and so forth, starting from the discovery of X-rays and all the way to the development of synchronous radiation science at the end of last century. So what's coming next? We are continuing to build a very powerful machine for the production of X-rays, increased brightness, increased coherence at the ESRF and the European X-FEL here in Europe, but in many other places in the world. And what we are being challenged to look at, you know, more and more we are going into what we call the nano world, where microscopy and imaging activities are more and more coupled to the typical X-ray science activities that have characterized the last century X-ray science-based discoveries. And we use these techniques in order to look at hierarchies, look at the way in which structures develop from the single atom all the way up to the macroscopic observation that we make. And again, this has major impact in bio and nanotechnologies, in highly correlated system, on the origin itself of condensed matter, and in particular more and more non-equilibrium matter. So what we can call is that the next decades are going probably being characterized in trying to understand better complexity and how length scales couples to each other. And that's where synchronous radiation is going to continue to have a major impact. Major impact that is seen today and will continue in many areas of application, among which the one that is discussed during this workshop on cultural and natural heritage. And the game is always the same. Try to link function, properties, and atomic structure for imagining new materials, understand old materials and processes. And this really explains what we have today, this incredibly rich synchronous radiation science landscape that has developed on what we call today third-generation sources. And the ESRF, this facility that is based on international collaboration, was the first one that came to function in 1994. And since then, all the other facilities have been built, often on the success of the ESRF or even improving what can be done at the ESRF. And why this is the case? Well, because these synchrotron sources are able today to provide what we call brilliance, the way in which we characterize our sources, has as many photons as possible in a source that is as small as possible, which is about 100 billion times more powerful than what you can get in a laboratory or in a hospital. So all these synchron facilities serve nowadays about 50,000 users. This is the largest scientific community existing in the world. And so this is basically the status quo. And since a few years, many reflections at the world level have been discussing what is the next step. How can we make things even better and reach out in areas which today are not accessible or are of difficult access. And again, the topic is how we can couple better and more efficiently X-ray imaging and microscopy to understand complexity at the nanometric level. And on that basis, the ESRF has started in 2009 what we call the upgrade program, which has been centered on two key aspects: the instruments and the source. Instruments of new generations that can help with all the infrastructure that goes with it to measure better at the nanometric level, and also study whether storage rings with much improved brilliance for X-rays are possible. This was the first phase that was delivered in 2015 and represented for the ESRF an ad hoc investment of about 180 million euros. It was successful because 19 new beam lines were constructed, but also a key idea for a much improved source came out in 2012, 2013, which materialized very rapidly in what we call today the extremely brilliant source that represents, again, an investment of 150 million euros and is centered on a new, first-of-a-kind generation of high-energy synchrotron sources. So what this source is supposed to give you? If you look today, the big asymmetry of a storage ring, which, as we know, has a very small beam vertical, but has a very big electron beam horizontal, because it's about 1 kilometer long. This intrinsic asymmetry is reflected in the source that we typically produce with third-generation sources, where there is roughly a factor of 1,000 between the vertical size and the horizontal size. So the key question is, can we go from here to there? Can we squeeze back all these horizontal X-ray, all this horizontal source into a source that looks more and more cylindrical? And this has been a big challenge, in particular for high-energy sources, and I will not go into the details, but in 2012, this man, who is also the director of the Accelerator and Source Division here at the ESRF, came out with a very, very smart idea that indeed will allow to produce this kind of source in the future in a quite routine way. If applied to the ESRF, will give you 2 order of magnitudes increase in brilliance. And we started in 2015 to construct this source in parallel with operation that came to end at the end of 2018, 2 years ago now. We started then to remove the old storage ring. We did the civil work in the tunnel, and we spent 2019 to mount this fantastic new source, which was installed according to the timing and according to the planning by the end of November of last year. And now it's time for commissioning. And in fact, if you look at the screen, since a few days now, in fact, since the 28th of November of last year, we are entering into the final phase of this of the delivery of this new source, which will provide again USM user service mode operation in August of this year. And we started at the end of November the commissioning. Will be followed in March, as you can see here, by the restart of the beam lines. And it's not the 38th, it's the 28th of November. I apologize. Already before at the end of last year, a key result was obtained on 15th of December, was accumulation. You can see here, 0.57 milliamp. You can see that the beam was stored and accumulated. So the key concept of this extremely brilliant source work. And last night, we resumed, after the winter shutdown, operation on the 16th of January of this year. And last night, as you can see here, and as you can see in the screen, we reached 30 milliamps on the storage ring. So we are, in terms of current, still a factor of 5 below what is the design parameter. But this is an incredibly fast commissioning. We have time until the 2nd of March to deliver 50 milliamps, which we consider as the one of the key parameters to restart operation with beam lines. So this is a great success that puts back the ESRF with performances that are unique worldwide, and again is leading the way to a major revolution in synchrotron science, because as of today, there is about 15 projects worldwide, some of them already in an operational phase, like the APS in the US, PSI and Trieste here in Europe, and an effort also for a greenfield source in Beijing, in China. And the ESRF will restart by the end of this year with about 45 beam lines, which nevertheless, this big success will put the ESRF in a quite unique position, the place to be for the 5 years ahead. So the next big issue is, of course, science. This is, in bullets, the science program that has been developed by the ESRF community at large. Is very much aligned with the Horizon Europe programs. And among that, you can see that a key point is humanity and world cultural heritage, to which this workshop is dedicated. And in fact, this workshop concludes a very powerful activity that took place during 2019, in which 21 such events have been organized in basically all areas of application of synchrotron science. And this cultural and natural heritage at the ESRF EBS workshop concludes this series over the last year. And I am really excited and grateful to you for being here and to help us in shaping the facility and prepare all the tools that you will require for a successful research program in the years to come. So I leave you now with Marine, and I thank you for your kind attention.
Thank you very much, Francesco. Okay. Does that work? Back. No.
All right.
Okay, that's how it works. Thank you very much, and thank you all for being here. So I will start with a brief introduction and some acknowledgement. I promise I will not be too long, just to give you a background of the idea of this workshop and also the objectives and the scope. So the idea indeed came to a few of us, in particular Pierre-Olivier, Camille and I. We were at the TechNart conference last year, and we enjoyed a lot this conference, and we saw that it has been a while since such a conference or workshop has been organized at the ESRF. The last one was together with CNRS SR2A in 2005, and we were thinking that it could be good to have the community meeting together, discussing on all the more so taking into account the coming EBS. And as Francesco mentioned, there is this series of EBS workshop. So when we were back, we invited Catherine, Paul and Niels to join the scientific committee and to discuss about such a workshop. So we proposed the idea to have directors of research, Jean and Harald, and they supported the idea. So they supported in particular by giving us assistants, ESRF assistants, and one more particularly, Catherine Fletcher. You may probably know her name because she sent you maybe 20, 30 emails, 40, 50, it depends on your level of reactivity and if you answered or not. And later on, Catherine was assisted by Chantal and Anne-Françoise. So I really want to thank her and to thank them for their huge effort in making this workshop feasible. And then we thought, okay, we should have a scientific program. We should invite speakers, keynote speakers. So who could we invite who are representative speakers who know well Synchrotron, ESRF, but also other facilities, and who could give inspiring talks and also projects in the future. So we invited Letizia Monico and Sophie Sanchez, Koen Janssen, Lee Berger, Vincent Fernandez, and Victor Gonzalez. And as you see, our idea was to present both cultural heritage, so you see that Koen is painting, and also natural heritage, and Lee, you have your favorite fossils in your hands. And then we were thinking, okay, we will be at the ESRF for 3 days, but could we have something out of the ESRF? Could we have a kind of social event downtown? And we contacted Grenoble Museum, Musée de Grenoble, and they agreed to have, let's say, coordinated event. This will be on Thursday. So there will be a public conference, a general conference in French, for those of you who speak French. And we will have also private access to some rooms in the museum, and we will have the conference dinner in the museum. It's a beautiful patio, so it should be a beautiful place, provided that we manage to go. Because I just learned this morning that exactly here, on Thursday at 5, apparently there will be a strike action. So I really hope we will manage to go somewhere here and to reach the museum. So all my apologies if this is difficult to go, but we will do our best. So 6, I wanted to thank Europe, because you may have noticed that we managed to keep the registration fees pretty low. And this is in particular thanks to the support of Europe through the project Streamline here, which is in the frame of Age 2020 Research and Innovation Program. And you will know more about Streamline on Friday. You will see what is behind this word. 7, I wanted to thank the Business and Development Office who gently offered the pens which were offered when you registered. And last but not least, I wanted to thank you, because if this workshop is a success, this is mainly thanks to your presence and also your participation. So really get the idea that this is a workshop and we are here to discuss. So if the speakers agree, I would say, talks should be really interactive and ask questions, discuss, and so on. It's that we are not at a conference, we are really at a workshop. So the idea is that expert users can help newcomers in understanding what they can do and develop ideas and so on for the future. So a few words about you. Where are you coming from? So I was very happy to see that 2/3 of you created, I hope successfully, SMIS user account, meaning that it is the first time for you that you are here at the ESRF. So that for us it's a very good sign, meaning that of course we have our regular users, but we also have new people and possibly new users in the future. And also a very positive sign is that you are coming from all over the world, which I think is very good. But of course most of you are coming from Europe, and you see the good players, let's say a strong team from Antwerp, Italy, and France, which is a bit normal because it's closer. What about the program? So today and tomorrow we will have many talks. We have tried to sort them in specific sessions about paleontology and more cultural heritage. Tonight we will have a poster session and an apéritif dînatoire, buffet dinner. And before that there will be a poster clips where students will be invited to briefly present their work. The same for tomorrow, and so tomorrow afternoon there is this event at the museum. And on Friday, so the program is a bit different. First we will start with some tutorials and practical, and then there will be presentation about new instruments available together with a new source in the frame of the ESRF upgrade. And in the afternoon, we will discuss all the challenges associated to these new instruments. And for those who would like to stay a bit more, we have proposed this visit of Grenoble street art. If you want to stay over the weekend, of course you can go to ski, but if you want to stay downtown, I can only advise you to have a look to the Musée Isère website. And in particular, there are 11 Isère department museums which are free, so do not hesitate to go. And I just listed a couple of ongoing temporary exhibitions, so one on Nichols, one on Rose Valland. This exhibition is beautiful, about the photographies of Vivian Mayer, and also a watercolor exhibition. And all these museums are at walking distance from Grenoble downtown. And if you want to go back home with some souvenirs, I have been advised that at the tourist office there are things that you can buy. When you registered, so you were given an envelope and a badge. The badge, it's absolutely mandatory that you keep it with you and that you wear it, because it will be the way you will access the canteen. And tomorrow, it's absolutely necessary that you have your badge to enter into the museum. If you don't have your badge, you will not be allowed to enter into the museum. For those who would register to the museum event, there was a tram ticket, so keep it for tomorrow. Otherwise, I mean, we don't want to have tomorrow hundreds of people buying a ticket just before the event. If there was a red or a green card at the back of your badge, this is because you have some allergy or you are vegetarian, so keep it with you and put it in front of you tomorrow at the museum as a workshop dinner. And this is just to wish you a Happy New Year and to welcome you again. And again on Friday there will be more information about street art visit. And last but not least, if you don't know what to wear tomorrow, take this into account. It's a bit cold in Grenoble Museum, so be prepared. Voilà, you know everything. And last thing, so you may have noticed that we have, if you were not here this morning, I just repeat it, you may have noticed that the event is live streamed on the YouTube. So first you can spread the information, you can tweet as much as you want, and if you don't want to appear on the videos, we agreed that those who would not like to appear can just sit at the back of the auditorium. And also when you want to ask questions, please stand up so that we can see you more easily. And I think that's all the things I wanted to say. And I will let the floor to Sophie. Yes, please, can you come in? So Sophie Sanchez, who will be a keynote speaker tomorrow, will be chairwoman for the first session of the afternoon. And the first speaker will be BERGER.
Thank you, Marine. Thank you, everyone, and I'm very happy to be invited to give a talk here and be chairman today. So I will invite BERGER to give his presentation on Australopithecus Sediba from South Africa. Yeah.
Thank you very much. Does that work? Yes, thank you. Thank you very much. It's a great pleasure to be back here at the ESRF. In fact, I'm going to give you two types of ancient history lessons today. One about the things that I study and some of the both old discoveries and new discoveries, but also one that goes back into the ancient history of the ESRF, where 11 years ago I began what would turn out to be one of my most successful science programs. And I would like to share that with you, its origins, look at some of the results of the work that we did between 9 and 11 years ago, the relevance today, the productivity that came out of that. Then I'm going to show you some sort of new secrets and new things that my colleagues and I are incredibly excited for the opening of this new beamline, and hopefully give you some inspiration for some of the things that you can use on this extraordinary new source that's being developed, but maybe more importantly, the new pedestals that can take weights up to 300 kilograms, which just happens to correspond with a bunch of very heavy discoveries that we have made down in South Africa. My journey with the ESRF began with the discovery of this rather unassuming site, a site called Malapa just outside of Johannesburg, that I discovered using Google Earth back in August of 2008. It was at a time where we thought that there were no new major discoveries to be made. The place had been searched over. The site was very unassuming. This is actually the very first picture that I took of that site as I walked up to it looking at geological maps. A few minutes before this, I had turned over a rock, and in the back of that was a wonderful fossil, but it was an antelope fossil, which was pretty much what I'd spent my career finding. Prior to that, but remarkably, this little hole in the ground was just 1 kilometer away from where I'd spent 17 years looking for these ancient human relatives, some of the rarest sought-after objects on Earth. This site is unassuming. It's one of the smallest sites that we've ever discovered out there. This was, by the way, 10 years ago, super high-tech, expensive technology that we applied at great cost. You can do a better job with your iPhone today than this. But just to give you a little bit of the idea of the scale of this site, it's only about 6 meters across, and it's only about 4 meters deep, that which was exposed at the time. But what made it such an important site was actually my 9-year-old son and his discovery. On the second visit to the site, a few minutes after arriving, he went off the edge of that little hole and said, "Dad, I found a fossil." And he had found this little rock, and I almost didn't look at it because I thought it was going to be an antelope fossil or something completely unimportant that I'd found hundreds of thousands of in my career. But he had these remarkable fossils, and I know you are allowed to gasp at any time you see something amazing like this. You're not gasping. That is a clavicle of a hominid, of which I remarkably had done my PhD and was probably the world's only expert on. And when I turned that little concrete-like rock over, on the back of it was this canine sticking out. And you're still allowed to gasp whenever you see a fantastic fossil like this. That would change my life. That would change my life because I immediately knew that this was part of a partial skeleton within that. And at that time, they were incredibly rare. We began to prepare parts of it, and some remarkable things came out. There you can see part of a mandible on the right, that's an ulna, and some ribs that were coming off. And at that time, we had several blocks, had exciting potential fossils. We decided to move into the sort of radiation sciences. My wife is a radiologist at Johannesburg General Hospital. And so with a possible fossil, I snuck the rock down there one morning before patients were due, ran it through the scanner, and saw this image. That image was an extraordinary image. It's an image that, in fact, probably had never been seen by any scientist in the history of the search for human origins. That's a skull that you can see in cross-section, entirely contained in this tiny block. We could only see a tiny fragment of it that had been exposed by preparation. This made us rather excited. It also made us rather cautious, because no one had ever had the opportunity to stand away from a discovery like this, not just take it all out and make a showpiece out of it. And so there was discussion about how we would handle this skull, as you'd see. And you see that we prepared the top of the skull, but we left rock below in place for future generations of scientists to examine, and we underprepared much of this fossil, not exposing the teeth largely at this time. This would lead also to the discovery of more skeletons. On the right, you see the skeleton that Matthew discovered. On the left hand is one I discovered a few weeks later. In the ensuing journey over the next several years, we would discover up to 6 individuals, but by hardly trying. Quite literally, as we opened up a new area of the site, we would encounter either another individual or more of these remarkable skeletons. That's when my synchrotron journey began, before we decided to publish it. Before we decided to put this out to the world, I wanted to get a better look at that, and working with Paul Tafaro and the great teams here at the ESRF, we brought this skull. It was one of the first time a major hominid fossil had been transported out of South Africa with all the government security you can imagine to actually do that, and perhaps the first time in history an undescribed fossil that was intended to be a holotype, we knew it was a new species, was transported out to undergo work in this, because the scanners that we had to look in these were woefully inadequate at the time and couldn't actually give us great imaging of this fossil. We also brought other material, including postcranial material. And I'm rather glad we did, with a much darker-haired Paul Taffero, and I had both more hair and darker hair at that time amongst others. We began to work with this material on the old beamline and began to get extraordinary results. This is an external look at that material, but really it wasn't the external look. Although surface scanners were not common at that time, it was really the ability to do things like this that were the first parts of what we began to see. The ability to look at every level, at measures that no one had ever looked inside of an ancient human relative before, imaging it in a way that was not only incredibly valuable scientifically, but these sort of emotive images entranced the public with the idea of this new technology that we could use. In fact, 60 Minutes followed us to hear the news show in the United States to film us as we undertook this one-of-a-kind experiment. The images are extraordinary that came from that work. They've been used in both downgraded levels and upgraded levels by our teams of scientists over the years, and are still used today and are still considered probably state-of-the-art images. Papers would appear in major journals on brain morphology, internal morphology, the dentition of these, of Sediba, and others that would really allow us to do something that others hadn't done before, including put the skeleton together, begin building what they look like, which would ultimately result in reconstructions of locomotion and the physical abilities of that. I was living the scientific dream with my colleagues. We had 3 special editions of Science over 4 years. To date, over 18 papers have appeared in the journal Science on Sediba, 1 in Nature, and over 80 papers in refereed journals have come in the last decade since we published in April of 2010. It has been an extraordinary scientific achievement, and a lot of it, a great deal of it, based upon that initial work, that initial imaging that we created here at the ESRF. But we also had a public use for that data, and I want to speak strongly to those of you who are in the cultural heritage, paleontology, paleoanthropology, because what these images, what those remarkable images you saw, and many, many others that we created coming out of this synchrotron scanning, became images that were used all over the world and in many public spheres, inspiring artists to create work, inspiring other scientists to do better science, inspiring the public to engage with these fossils, even inspiring Stan Lee to make Sediba the origins of X-Men, you see over on the right, and which was a great way to reach the public when you think that a fossil that newly developed actually gained that sort of public appeal. And I think a great deal of that was due to the incredible images that were produced here that were useful for both science and for the public. It also allowed Sediba to be named, in fact, in December of last year, as one of the 10 most important scientific discoveries of the last decade. That makes us very proud to see fossil hominids, fossils of any kind, that are making those sort of lists, along with the great other scientific achievements that are being done in both space and at places like the ESRF. I want to throw some statistics out here, and these are not meant to brag. They're meant to inspire you to use these beamlines and to do this kind of work. As I just said, it was recognized as among top 10 scientific discoveries of the last decade. We have put out more than 80 peer-reviewed papers, and right now Sediba has 525 citations, the original paper, and that's, well, many physics papers and stuff have more. That is a huge number in that period for a paleontological paper. More than 150 collaborating scientists are on this, making it one of the larger scientific projects in the world, certainly in the paleo sciences. We've delivered more than 125 keynote addresses and won 29 prizes and awards issued to scientists and papers that have been produced off this. Over $345 million in value of coverage has been developed, and South African government obviously likes that a lot. So does my university, and so should the ESRF off things like that. More than 8,000 popular articles have been written about Sediba, and a reach, and that's the number of hits and number of impressions it's made around the world, of more than 30 billion in 10 years. And those are numbers that are important for you to understand, because it's just a fossil. It's a fossil of an ancient human, but it's part of the way in which we can do science with this type of data in a rapid way and in a public way that allows us to have that. And now I'm going to talk about new discoveries that I hope to be bringing to this new beamline, Mr. Director, in the next year and a half or so when they open. One of the unusual things and coincidences is when we started making really big discoveries. Not big in the public idea, but big in the rock idea. Like this particular one, which you can see is a very large rock. That rock at that time weighed about 60 kilograms. Inside of it, we could see sticking out the back of it, that is the mandible with a tooth of an ancient hominid, which quite interestingly happened to fit right onto a piece that we'd found at the site that fit onto the jawbone of that first hominid that Matthew found. So we knew that there was a good chance there was the rest of Karabo, the first hominid from Malapa, inside of that. We tried again in my wife's facility at the hospital, when no patients were there, to actually scan it, and we found to our pleasure that this rock, this gigantic rock, which was over 70 centimeters across and 50 centimeters deep, was beautifully translucent to X-rays. To clinical X-rays, you could actually see the bones in them. I'll just slow that down and give you a little picture. You can see the bones were appearing, but it wasn't clear enough to do anything major with that at that time. But of course, there was no synchrotron facility, no beams really on the planet that could take something of that weight. When we prepared part of that block in order to see that there was indeed a hominid skeleton, there was a spectacular one inside. It in fact appears to be the entire rest of the first hominid that we discovered at Malapa, which luckily is the type specimen. That's one layer of it. There's an entire another layer we can see in clinical X-rays under it. But again, it was never going to be scanned in a synchrotron. The biggest objects that we were going to put in something like this were sort of the size of that skull. And so we moved heaven and earth to try and work on this. We actually took it to the United States, to one of the largest micro-focus CT scanners in the world, and one of the most powerful ones at Lockheed Martin in Dallas, Texas. And we tried to get images inside of this rock, and they didn't look very good. They failed. And we're not sure why they failed, because the Malapa material is superb in synchrotron, it's superb in clinical X-ray, and it doesn't work in any of the micro CTs that we have. And so we are very excited, Mr. Director, to potentially bring a large object that seems designed for this new beamline and should be a perfect working case to see a very important fossil that we may then leave for future generations of scientists to save data within that. This is a spectacular discovery. What you're looking at there was that area that was blackened just above the skull of that, the holotype of Sediba that Matthew had discovered. What that appears to be is fossilized skin, dating to 2 million years before present, including venous structures, the base of hair roots, follicles, and other things. We, again, have attempted to use our own micro-focus CT scanners and others, and the imaging isn't great, but again, I have great hope because this looks like the kind of thing synchrotron was designed to see. And if so, we may be able to look at things like hair follicles, whether it's fur or hair, and other amazing things that I think no one ever thought would come out of a hominid. And so that's on the table for the next generation of these beamlines. And of course, we've continued to work. I haven't spoken about Homo naledi. We've continued to work within those systems, those extraordinary underground systems that over the past 5 years, just outside of Johannesburg, we've recovered more individual hominid remains than in the entire history of the search for human origins on the continent of Africa, from one locality, from one site system. And we've been continuing to work in there, and we've encountered problems. Problems that can't be solved because the material is not coming out in small fragments. It's actually coming out in big pieces like this, where you have large samples of material. We're now at over 2,500 individual remains. It's actually probably closer to 3,000 based on new discoveries. Paul Taffero and others in this room will be thrilled to see we have lots and lots of teeth at different ages, and synchrotron gives us the option of actually sectioning certain teeth without cutting teeth. believe it or not, to look at growth and development and rates of growth and other factors, we have traditionally destroyed these precious fossils to do it. And there are still studies that need to do that. But one of the advantages of synchrotron, I certainly believe this new beamline will give us, is less damage and the ability to more carefully choose these associated groups of fossil teeth that we've discovered. And then we have spectacular fossils like this from the Rising Star Cave System. I know you're all shocked when you see a lump like that. That is a very special lump, though. It's one of 3, recovered in situ, as we noticed that there was a feature that seemed to be cohesive in another chamber, a different chamber from the Dinaledi chamber. And so we managed to take this feature out in 3 pieces. Had to be 3 pieces because no object or human can exceed 18 centimeters to get in or out of this cave. You have to go 12 meters down an 18 centimeter wide chute to get into it, so we could not take an object larger than this. And when we put this back in my wife's medical CT at the hospital, we saw beautiful things. Beautiful things that surprised us in their completion and complexity. That is part of an articulated dentition, an upper and lower of a child that's likely something like 10 years old. There appear to be parts of the skull and other parts. And when you begin, and when we tried micro CT, this doesn't fit within a micro CT scanner. It's too big. It's too big to fit in any type of conventional micro CT scanner that we have, but there are things to be seen in there. This is just a rough preparation of those clinical CTs of the stuff that surrounds that little maxilla and mandible. And I would point to things like the foot that you can see here, articulated, the hand that you can see right here that is articulated and in a death grip. And all of these are bones, and there are other finger bones. There are actually lots of ribs and stuff. There are also beautiful sets of teeth of maybe more than just one individual in this. An extraordinary thing, and we again need this new beamline to actually see into it, because we don't want to remove this. This is not a hard rock situation like Malapa or Sediba was found in. This is just in dirt. And if we remove this packaging, we potentially lose all of that extraordinary information that may be recovered from a situation like this. And it also tells us we need to leave more of these features and such intact. There's a lot of information to be got from this. So I'm going to end today, but I want to say that I think we are in one of the most exciting ages of discovery and science in cultural heritage and study of both deep paleontology, deep time, and the deep human journey. Because not only are we making more discoveries, and we've clearly demonstrated that there is more out there to be found, but we've done it in an age where we can do things and extract information that scientists 20 years ago couldn't dream of doing. And places like the ESRF are at the very front of that. You're looking at a leader of one of the largest teams of scientists in the paleo sciences in the world, and we have experimented with all the modalities, all the X-ray modalities. And while many of them give brilliant results, that the synchrotron results we achieved even 11 years ago are still the gold standard for that. I think you're going to hear that a lot during the course of this conference, but I hope that we've been able to give you some inspiration around the potential, both the output potential of data from places like the synchrotron, the publishability of data from the synchrotron, the excitement of data from the synchrotron, and also ways of using new objects that nothing could deal with and would have been destroyed in the process of preparation that this new beamline will offer us. Thank you very much.
Thank you so much.
It takes a moment, I think.
Does it work? Yeah, perfect. Thank you so much, Lee. That was really, really exciting. So I would like to know if you have any question to Lee. Yes?
What is the composition of the soft tissue fossil, the scalp section that you showed?
We're not really sure. We conducted Raman studies on it and other, X-ray diffraction. What it appears to be is it was likely to be mummified skin that displaced itself in the preservation process. The fossil was preserved in calcium carbonate very quickly, potentially due to insect activity, interestingly, around it, which then pulled it away. And there seems to be some silicification that occurred in there, but we're not exactly sure. And some of the potential that we have on potentially even other beam lines as we begin to explore what the causality of this is. I expect, without knowing exactly how it happened, that's going to be part of the study because we can't see beyond the back. I suspect that this is not an uncommon occurrence. On the back of that large block we're going to be bringing is an antelope fossil that clearly has skin on it. And there may even be muscle tissue preserved within that. We have from the other hominid, at least one other hominid, what appears to be skin preservation, very convincing skin preservation. I suspect that what happened in the past, because of the way we are preparing things manually in large areas of paleontology, we were wiping through that evidence because we didn't believe it existed. I think that's true in dinosaur paleontology. Well, I know it's true in dinosaur paleontology. I think it's true in many others, and it's probably, I think that one of the values that things like synchrotron are going to offer us, and there are, we can speak to the downsides of over radiation and stuff and talk to that in a moment, but the upsides are being able to conserve situations like that for either future modalities or future scientists.
Thank you. Any other question?
Yeah, it was great. I mean, really exciting. There's so much to do still. You can clearly see it. I have a curiosity. I remember that one of the hypotheses for A.Sediba was a child that fell into a pit. But it looks like now you have many hominids in the same pit. And also what I found quite amazing is, by looking at your fossil, maybe I'm saying something stupid, it looks like that somehow all the bones are broken and somewhat displaced from each other. Is this just natural? Because when, you would expect that, is this a burial? I mean, there's so many things one can imagine and ask.
Yeah. So the answer to that, surprisingly, is it was very easy to formulate hypotheses a decade or 12 years ago on how these things were, because we viewed these ancient hominids as much closer to apes than humans, such as that. A.Sediba is 2 million years old, and so we were looking for natural ways in which something could die. And so we were hypothesizing water holes and risking their lives. Now, in Sediba, Australopithecus sediba, there is some evidence that individuals, at least at or near the time of death, suffered falls, breakages of bones, forearm fractures. At least 2 of them seem to have those, but we don't know whether that happened after death, was the cause of death, or happened as some kind of fall like that. What we do know is that most of those hominids actually from Malapa are articulated and intact, or as close to it as most of us paleontologists ever dream of in our lives. This is a second skeleton. But the disturbance appears to be due to a phenomena that we're working on. We haven't deeply published it yet, but it'll be coming out in the near future, that most of the Malapa site was constructed by termites. That is, termites actually built calcium carbonate hills over top of these fossils, and that's what allowed the preservation, but also probably some of the shifting and disturbance. The rising star cave system, where Homo naledi comes from, is completely different. We have not found any evidence that they were killed by predators, that any of them have any significant injuries on them. They weren't killed in a mass death. They weren't brought in there by flood. They came in at different times. And my colleagues and I proposed at the time that the last remaining answer was that this incredible assemblage of now probably approaching 30 different individual hominids, and we're not even trying. We know there are more there, in 6 or 7 different locations, was likely due to deliberate body disposal. That seems impossible given that they have brain sizes just larger than chimpanzees. but they're at much younger age, at about 250,000 years approximately in that area, but people say that that's largely impossible. I think you're hopefully this year going to see some pretty extraordinary new evidence that looks into the hypothesis of why they're there and why they're like that.
It could be a bury.
That is a possibility I'm not going to say out loud on YouTube.
Thank you. Do you have any other questions?
Just a technical question. What was the energy of the synchrotron radiation and compared to the energy in your wife's hospital instrument?
Okay, so my wife's hospital instruments are running on standard protocols that we usually use a bone protocol on. So whatever, the energy differences have changed over the last 11 years. And we, by the way, run a weekly scanning program, scanning blocks, trying to make discoveries like that. Every Tuesday morning, we're sitting there with our patients in line, ready to actually go through. Paul can answer the energy questions on the skull.
This one was done in monochromatic at 96 kiloelectronvolts on ID17. It was 4 days of scanning for the skull.
You all heard Paul? Yeah.
96, yeah? Oh, say Paul maybe.
Yes, 96 kiloelectronvolts in monochromatic on ID17. Just for the fun part, doing that on BM18 in a bit more than 1 year, you can go to 350 kiloelectronvolts instead of 96. That was the maximum. And it would not take 4 days, but more something like half a day or even less for much better quality. So just a small detail.
Thank you. Any other question?
Thank you very much. Thank you.
Thank you. Thank you very much, Lee. That was really exciting. Okay, so now we will invite Dennis Voeten from Uppsala University, who will speak about another iconic fossil, Archaeopteryx. So we will now go back to South Africa, fossils, and invite Vincent FERNANDEZ to come on to talk about very large fossils. Vincent's coming from London. Thank you, Vincent.
Is it working? Yeah, okay. Ouais, okay. Merci. Thank you, Sophie. Hello, everyone. So I'm Vincent FERNANDEZ. I've been spending quite some time at the ESRF. Actually, I've spent 8 years working with Paul Taffero, if you have seen him this morning. So there was a lot of work that we've been doing together, trying to scan fossils. And in fact, not that I was particularly looking for it, but the history of scanning fossils was just brought me to scanning bigger and bigger things. And most of these things from South Africa. So yeah, I've been doing my postdoc in the same institute as BERGER, and I've developed a lot of collaboration, and it just increased and increased and increased. So the 3 collaborators I've been doing this project with are all from this institute, at the Evolutionary Studies Institute in South Africa. So yes, we've been scanning a lot of fossils at the ESRF. And in fact, they've been for different shapes and sizes, all sorts of animals, and with different questions. But the question was, why do we come here? Why do we? It's quite unsettling at the beginning to see so many paleontological projects in a synchrotron. So I thought I would explain a little bit why we come here, not to being too long, because Paul did that as well this morning. So there are a few parameters of the synchrotron beam that makes it a bit different to come here, a lot different actually. There is the brilliance, there is the geometry of the beam, and there is the coherence. The brilliance means you have more photon, so you can go faster, or you can have better results. It's like when you have more light, when you take a picture in broad daylight or at night. If you have more light coming in, it's a lot easier to take a more beautiful picture. The geometry, like in laboratory sources, you have a conical beam, so you have a distortion of your image, and you will see that there are some problems when you want to zoom in your object. And the coherence, it's for phase contrast imaging that was covered by Paul, and I will show some other examples as well. So that's a relatively old slide that Paul was using to compare a laboratory microtomograph and synchrotron. So which one is light? Yeah, so this is done with laboratory source, and this is done on ID19. And you can see that the image is a lot clearer because you have more flux, you have more photon, so you have a better image. And because we were able to use a monochromator as well, we get rid of beam hardening, the white rim that you see on that image. So the technology as well has evolved on the laboratory sources. And so this is, now that I work at the Natural History Museum and I have to work with a laboratory source, I can do some comparison between more comparisons. Not that we have to, but basically, if I have a comparison, it means it failed at the lab and we have to bring it to the synchrotron. So in this case, it was a tiny dinosaur from Wales, and you can see there is a mandible with the tiny teeth and some vertebrae here. So I did a relatively long scan, not the longest I could do, but in fact it didn't work very well. So, and just to show you that when I say we have more flux and it's faster to get with regard to one slice. So the beam with the machine we have at the NHM is relatively large. We can image this whole thing in one go. It takes 3 hours, but we can get all that. When we brought the same thing and do it on BM5, the beam is really small. And so if we want to cover the same area, we need 50 scans. So even if one scan is a lot faster, in the end you need 20 hours to do the whole thing. So it's not necessarily a lot faster for a relatively big object. But when you look in 3D and you look at the result, spending a bit more time, so that's with the lab source, and this is with the synchrotron. So the image is a lot sharper. You don't have this blurriness, you don't have this noise in the background. And here you can clearly see where the bone starts and when it ends. And if we go a bit further into the rock, you can see the teeth. Yeah, it's like, it explains itself. The quality is a lot better with the image done at the synchrotron. So more flux, better images, and even if it takes longer, definitely worthwhile. If we look on the other direction, yes, same story. Like here you can virtually extract individual teeth if that's something you want to do. Here you can barely see what's going on. With the geometry of the beam, the part where it's difficult to zoom in. So at the Natural History Museum, I was asked to scan one of these Aepyornis eggs. So it's like there are really big eggs from this extinct bird. And the problem is, because it's a conical beam, the magnification is done by changing the distance between the source and between the sample, like moving the sample between the source and the detector. The closer you get to the source, the higher the magnification. A bit like with a torch lamp. If you put your hand really close, the projected shadow is really big. So here, if we want to see microstructure of the eggshell, we have to go as close as possible, but because of the size of the egg, and because we don't want to break it, that's basically where I had to stop. And I can only focus on the polar region of the egg. We had some information. We see a little bit what's going on, but clearly that's not enough if you want a true microstructure of the eggshell. So I didn't bring this one to the ESRF, but just to give you a feel of what you can do when you want to zoom in an object. Well, I guess, yeah, Dennis did that very well, actually, when you want to zoom in really far. This is another example. This is a mammal-like reptile. And here we can see the incremental layers of the teeth at sub-micron resolution. So here, but the object is smaller, but you can really zoom in because the equipment is really far, so it's really not a problem at all. And the coherence, I think a good example is the work I've been doing for my PhD quite a few years ago now, but it showcased very well why the synchrotron is also really useful for fossil in general. So as Paul explained, because of the properties of the beam, if you want to use phase contrast imaging, and you only have to increase the distance between the detector and the sample. And if you look in detail, and if you want to make some comparison, so this is, yeah, I forgot that part. So my PhD was to study these tiny fossil eggs. So they don't look really well preserved, but we knew that there were some tiny embryos inside. So we were very excited about them. And we had no idea what they were. But we thought they were dinosaurs. But so when we scan this tiny egg on a lab source, well, it looks like this. It's not that bad. We can see that there are something here, here, here. It's like the image is a bit noisy, but it's like I've seen worse scan, way worse. When you bring it to the synchrotron and you apply the same technique, absorption synchrotron microtomography, so the detector and the sample are really close, it's a lot better. It's a lot sharper because of the flux, and you can recognize the structure a lot better. But it's not amazingly better. Increase the distance between the sample and the detector, and it looks like this. All these tiny things are bones that are completely invisible if you are based only with the absorption, and when you let the phase contrast kick in, then you see all these tiny bones everywhere. And then you have your magic happening. So when you want to study a fossil eggs with embryos, you have your recipe, your eggs à la synchrotronoise, if you will. You just scan your eggs. It takes 30 minutes. I think it took 12 hours, actually, back in the days. But now it will take just half an hour, maybe. Then you spend a few months segmenting every single bone one by one. So then you can do your 3D jigsaw puzzle, and then you reposition everything, and you can study your animal. You can 3D print it, you can magnify it, and then you can study it as if it was a classic specimen. And we discovered that this animal was in fact a lizard and not a dinosaur as we thought it was at the beginning. But so scanning eggs gave a lot of ideas to a lot of people, including some people in South Africa. So because they have this beautiful nest with dinosaur eggs, so they know there are dinosaur eggs because they've prepared one of them, a few of them actually. So it was discovered a while ago. And here the case is a little bit more difficult because it's bigger than the tiny eggs I was doing. And they are all in a tiny nest, so we can't extract just one and scan it. The more you add material, the more difficult it gets to get a nice image. But still, so we the idea was to scan each egg one by one and then to focus on tiny parts. And you end up with relatively similar results. So this is a very preliminary result of this study. Now the project have moved on, so you can do your spinning skull as well. It's pretty, but you can push so they knew what this dinosaur was, so that was not the point. We knew there was one, we knew it was a dinosaur, we know the species. So here the question is, what can we do with this data? And you can push the study a bit further, forget about the spinning skull, and compare with modern material of archosaurs, and trying to get a feel for the incubation time. So if you compare with turtles, crocodiles, or chicken. So it's not only just for trying to identify something. You can really push the study a bit further with this kind of data. Put the bones back in their original position and compare the ossification pattern. And because it works, gives people idea, like again the people from the ESI. And because you try something a little bit bigger, they push it. Like, can we do just a little bit bigger? It's like, yeah, probably. So they send a picture. We say they wanted to scan this dinosaur, which is called Quabasaurus. And so you have part of the skull. It's a bit destroyed, and a vertebra and a forelimb. And the idea is that we have all these bones, and we don't really understand that well that dinosaur. So it's a way of, can we scan it, put the bones together, and finally get all the information that we need? And we did that in the course of the ESRF summer school in 2016, so with Victor here, and we did that on ID16. So it was a very intense project because within a month we had to scan it, reconstruct the data, segment it, and present the data at the end of the month. But yeah, Victor is a very diligent student, and he managed to pull that off, so well done. And so what can you do when you have something like this? Is it starting? Yes, it is. So you can isolate a part of the skeleton, and you can see the face that was hidden inside the rock. So now you have your bone in 3D. You can have access to all the features. And so that was with a limb. We'll pass on the vertebra because we can look at the vertebra as well. But one of the regions of interest was the skull as well. So it's all in different pieces. We wanted to do a higher resolution of the higher resolution scan of the skull. Problem is, it's a big rock, so it was not that easy to focus in one go. But because we like challenge, we decided to give it a go. So instead of scanning it vertically, this time we put it flat, because it was prepared. In fact, there was not that much material where the skull was. And so if you look from the top, what we did actually is 4 scans that we ended up merging together. So it's like a scan is basically a cylinder. So here, instead of you doing your stacking, like just increasing the distance, doing more scan and stacking them, we did scan and moving the specimen horizontally, and we can just put them back together. Just took me like a month to develop that, but anyway, it's worth it because the data, you spend some time, but it's worth it because the data are really nice. And this is a first view of the work of Victor, so he's spending a lot of time segmenting each bone one by one, and we should see some more information about that in the future. So we don't have a lot yet on that project because Victor has been busy with something else. And so, we've scanned a lot of big samples, but mostly in the range of 15, 20 centimeters in diameter. And there are plenty of examples. There are Australopithecus Sediba. There is a burrow from South Africa as well, a bigger dinosaur that was done here as well. And one day, Jonah contacted me because he wanted to scan a dinosaur called Heterodontosaurus. And so he sent me an email, we start discussing, hey, I have this really cool specimen, it's nearly complete, it's articulated, and it's Heterodontosaurus. So I don't know every dinosaur because I'm not 10 years old, even if I'm a paleontologist, I have to Google them. And I look at it, it's 1.5, so it's like an animal that big. And it's like, it tells me I think it would fit into the beam. He knows, it's been there a couple of times, so he knows that what are the maximum thing. So if he's telling me that it's complete, articulated, and it fits, I was a bit curious. But so I say, yeah, I believe him, but how large it is? So he say, it's preserving 5 blocks, 30 centimeter long, and 16 centimeter in width. Like, yeah, I see the trick. It's not one big specimen, it's been cut somehow. And I would like to see a picture because it's always better to judge with a picture. And so he sent me this. And he say, okay, so each block one by one, so we do the math, we calculate everything. I say, yes, we can do that. It's going to take a week, but yeah. And so why is it like this? It's because it was found at the bottom of a riverbed, and there was a few bones sticking out. So the problem is when the water would return, it would damage the specimen, so it had to be excavated really fast. And in fact, paleontologists, they don't play much with brushes. When we have to do some work, we have to do it fast, and we use proper tools. So that's why the specimen was excavated like this. So in the end, we certainly missed a few parts where it was cut, but in fact, it's in proper blocks. It was nicely prepared. They actually prepared the underside of the rock, so you can study it in both sides. And the sediment is really just a few millimeters thick and with a bigger frame of rock around. So we bring that to the ESRF. That's not how we scanned it this time. That's just for the nice picture of the media. What we did was we thought about, so how do we scan that? First thing is we need several scans on the vertical axis with a 15% overlap. I will come back to that later. Because it extends the beam, the width of the beam on the horizontal axis, we shift the center of rotation on the side, so it doubles the field of view relatively easily. I say easily, I don't have to code the reconstruction algorithm. It's probably a nightmare, but for us, it's just moving the motor and done. And so we can fit the whole specimen in there. But the problem is the aspect ratio of the specimen. So it's really large, really long, and extremely thin. So we thought to get more, we can probably have more done. We can do more. We can have better data. So if we spend more time, we can probably scan 2 blocks at a time. That's what I want to say. And we thought we should probably fill the gap a little bit with aluminum balls, just because it's really the sediment is really too thin. So it will increase a little bit. It will be the difference between the width and the thickness will be a bit less different. And so put the other block on the side and put them together and just put a lot of duct tape everywhere, so it's not going to move for half a day or a day, depending on how long it took to do that. And yeah, there was some dense inclusion, but I will skip that. And this is not a fake media picture. This is the real picture of us seeing the data for the first time after 5 days of experiment. So we are completely tired, but they are all super excited. Jonah is like, whoa. And I'm like, because in fact, when you look at the data a bit closer, they look like this. So these ring artifacts are very nasty, and they're due to the fact that the specimen is really, really large. It's like, yeah, again, like probably 16, 18 centimeter. But it's enough so that when the beam goes this way, so you have ring artifact come from dust or impurities on your scintillator, the part that convert X-rays into visible light. So when you do your tomography, you take an image without the specimen, and then you divide that with your radiograph. So you effectively remove all the defect of your scintillator. When you have something that large and that dense, the problem is you are not seeing the defect at all through the specimen. So when you correct it, you overcorrect it. You remove something that you don't see anymore in the real radiograph. And that's why it's a nightmare. And so that's why we use the 50% overlap in the end. Because it means each part of the specimen was seen twice by different part of the detector. And hopefully, if it was in a part with a nasty defect or impurity or dust, there are some chances that maybe on the next scan it wasn't. So we could write a program that would select which part to take from the 2 scans, and hopefully that would solve the problem. Again, it was quite some time it took quite a few months to write that, but it went to that. And this is not perfect, but this looks a lot better than this we can deal with. This we have classic ring artifact correction, and it brings to this. So Jonah and Victor, like for months, they've been so, are the data ready? Are the data ready? And it was a bit of a nightmare, but one day I was finally able to send them that. And we were able to apply that to all the data, send all the block, reconstruct this beautiful dinosaur, and put them back to their original position. So yeah, it was quite delightful to reach that step. And because there are dense inclusion, it was very easy to threshold the data. The inclusion are actually only where the bones are. And so what you see here is not really the bone, it's really just the dense inclusion that are surrounding the specimen. And now, with all the data ready, so Victor has spent some time trying to segment each bone of this dinosaur. So he started in the rib cage because there is something funny going on. We should see that published relatively soon. It was resubmitted recently, so fingers crossed. And yeah, so it's a lot of work. It's a big challenge, but in the end, it's worth it, and it works. And then there were some other projects where we kind of hit the limit, and I will finish on that. So, and it's kind of funny because it's one of the projects I did. So I was scanning like burrow cast. So when you have a burrow, the animal dig a tunnel. In the fossil record, the tunnel is filled with sediment, so you have a cast of the tunnel itself. And you can have some animals that have been trapped by the sediment that was filling the tunnel. And it's funny, on that day when I was scanning one of the biggest rocks that was scanned at the ESRF, other people were scanning some of the tiniest stuff we can do on 1919. And it's actually, the people, so the team of Peralberg, and they have been a lot better than me because they already published that. It's a beautiful study on the origin of tooth replacement. I'm clearly not there yet because the data were really complicated. So first we had to ship the big burrow from South Africa. So they are about, yeah, that big. And we put it in a big barrel with pebbles to homogenize the attenuation. At least it was broken, so I could scan it in 2 parts. We used the germanium detector, which doesn't have the best resolution, but that was the only option to scan something 30 centimeter large. And we had 2 blocks. So the part in green is the part that was missing. I didn't saw that when I scanned this, but at least I have most of it in there. And we did another test on the region of interest on 1919 at 24 micron. This is the result on ID17 with the germanium detector. So we knew that there was a few bones sticking out, and here we kind of see, indeed, there is something inside this big burrow, but the quality was not there. We can't really work with that. But at least with this data, we were able to aim at a specific region of interest on ID19, much higher energy polychromatic beam, 24 micron. Here we can see the bones. It's not the greatest image, but at least you can kind of work with that. There are even some parts where you see nothing at all. And if you look at the data from ID19, you can see like all these bone fragments. So I spent a bit of time trying to segment this data. They don't look really nice because it's a bit difficult and I have to go through all the slices manually. But at least I had some information. This is part of a mandible from a mammal forerunner. And at least I am 100% sure that they have no teeth. And there is a big group of these mammal forerunner with no teeth, so it's like narrowing the identification. And based on the age, the size of the animal, and all, we have a tentative identification that this animal is Odinodon. Because in the project of studying a burrow cast, the first thing you want to do is who was trapped in that burrow, and then move on with why was it in the burrow, did he dig the burrow himself, and so on and so forth. So we are still, I would like to have better information to be 100% sure that this is Odinodon. There is a lot of work to get to go to the level of this this character, these diagnostic characters, but yeah, it's taking quite some time. So this is where we are, and hitting the limit of what can be done at the ESRF, and I was like, what is the hope for the future? Well, the hope is probably to have a beamline that allows to scan something like that decently. So with all the transformation the ESRF is going on, allowing some micron on larger sample, or imaging larger fossil, or at least because we kind of did it, but it was not really possible to exploit the data. So maybe properly do things of that size. With the increase in coherence, being able to properly use phase contrast at higher energy as well, maybe that would solve the problem and we can see the bone a lot better and help with the segmentation. And of course, the hierarchical imaging access, because at the moment it was always the point of we have to dismount the optic or move the sample to another beamline. And if you see something in one image, you just want to zoom in, and we could not do that before. But because of that experience, there have been a lot of development in that aspect as well, and it should be a lot easier to reach to do a relative large-scale scan and then zoom in region of interest. And on that note, I will conclude my presentation. Thank you, everyone, for your attention. Thank you, the organizing committee, for inviting me. And yeah, thank you.
Thank you very much, Vincent. That was really interesting. Any question to Vincent? No question? Yeah.
Thank you, Vincent, for a very nice talk. Can you say something about data analysis? Because it looks to me that with all this data and the features and so on, probably data analysis is going to become a major bottleneck in order to have an efficient use of this data.
Yes.
It's also true we wait so many years to have the data. We can probably wait many other years to fully analyze them, but humans are quite anxious to get everything done very quickly if they can.
Yes, it's true. So getting something scanned is not really the bottleneck anymore. And if you look at all these projects, so the dinosaur egg, the lizard eggs for my PhD, I was a PhD student. Kim and Victor, they've been doing this work with their masters and their PhD. So it's people who do this kind of work, is people, they have 100% of their time, almost 100% of their time dedicated to this kind of work, because it takes literally weeks and weeks and months to do this kind of segmentation. What we are hoping is jump in probably in machine learning to get more automated segmentation. So even if it would take days for the machine to work out the data by itself, if you don't have to spend your day yourself doing it manually, it would help tremendously for sure. I guess one of the difficulties that every fossil is different, so it's like the texture, the contrast is different, but people are working on it, so, and it's been very promising in other fields, so why not for us indeed?
There is indeed in the program a session tomorrow afternoon about deep learning, machine learning.
Thank you. Any other question?
Maybe, Sophie, if I can ask something?
Yeah, absolutely.
More as a chemist. For one example, you were mentioning dense inclusions.
Mm-hmm.
And can you just give me, what does it mean in terms of composition? Is there a strong difference, and what is it made of? And to which extent somehow probing more the chemical composition rather than just the density, which additional information you could get from the chemistry?
So we have, it's because I don't think I have, well, I think we do, if we come back, well, actually this one works. So here you have your bone, and it's very similar in density to the matrix, like what we see here. We see the vascularization of the bone, and the white part is a dense inclusion. In that case, I have no idea what it is. A lot of people would say it could be hematite or it could be pyrite. It's very common in fossil to have this mineral, but it's not always studied. We don't really look at what it is at the moment. which in some cases could be a shame because these are inside the bone, they are inside the vascularization, so they could mean something in terms of biology. They are certainly here because of the biological material that was here first. So they might contain some information, but it's something that was not very explored. But at the moment, really for us, it's been a hindrance for getting nice data. But I know in South Africa they did a few tests on Heterodontosaurus, and apparently it was hematite. But beyond that, beyond what does it mean? What does it mean in terms of preservation? I'm not sure there was a lot of work that was done on that.
But this is maybe something which will come more in the future, that our two communities, the natural heritage, the cultural heritage, will meet maybe more with combining more chemistry and imaging and merging these two approaches to learn more about this kind of materials.
Yeah.
Thank you. Yeah, go.
Just to say that it's worth noting, Per Ahlberg, Uppsala, that although you might look at it and think, well, this is an inconvenience. Actually, because the synchrotron actually copes with inclusions like this. If you put this into a conventional X-ray source, you'll get awful kind of sunburst lines there, and it just messes everything up. But we have a couple of specimens we're working on at the moment from the Devonian of Russia, early tetrapod material, where infile, or whether it's hematite or pyrite or whatever, but extremely bright material that is investing and filling the spaces of the bones is fantastically helpful because we get extremely good contrast between the bone and matrix, and you're able to model up very, very cleanly the surfaces of the bone. Areas where the bone is in direct contact with, as it were, normal matrix, much more difficult to work with. So, with the quality of equipment we have here, then this stuff isn't necessarily a problem at all, but can be a real help.
Yes, and well, in that particular case, it helped because that's the only thing we could see on the first scan, and it's true as well for Heterodontosaurus, where we can see almost the full skeleton with just a threshold. So it's not the entire bone, but at least we know it's a start for the segmentation, maybe. So yeah, it depends on the cases. Sometimes it's been completely impossible to work with, but some other time it's been indeed quite helpful.
Thank you, Vincent. Any other question?
If I may ask a second one, then. And a bit related to what Francesco asked about data analysis and so on. There was one picture where, we were with you at the beamline and we were getting results with you. And I was wondering to which extent, when data are acquired, you have already some result, because you were mentioning that data processing is taking a lot of time. And with this idea of zooming in, you need to know, you need to have a feedback. So is it because when you zoom in, you don't need this segmentation, you can immediately recognize, or you need to also to increase the speed of data processing in this strategy of hierarchical approach?
If we look at so it depends how bad it is. Here we did hundreds of scans to cover the whole blocks of this dinosaur. And when we look at the first data, they look like this, which is not something we can really work with, but we can see what's going on. We can see where, we can see the bones.
So typically from this, it's enough to know if you want to zoom in a particular region, it's enough. Okay.
And at least we know as well that this can be taken care of later. So it's not, we can recognize when something is is a problem that can be solved or not. But at least, this we can obtain relatively quickly after. When we do a full scan, so a complete scan takes 20 minutes. And to get the result, it probably, depending on the cluster, it would maybe in an hour you can have something, or maybe less. You can have one slice very quickly in a couple of minutes. So, but if you want a larger volume, it takes a bit more time. But it's relatively quick to have something of that quality. It's just the difference between what you can work with and just having a quick idea of what the data look like. But we need a fast response indeed from when the scan is finished to be able to get an image. And so far the workaround was to get really small scan, so they would be relatively fast to process in just a couple of minutes, and then we would know either to run a full resolution scan, or if we had to move the specimen, it's been the strategy as well. Like when we have to scan to aim for something that is in the middle of the rock and it's really small, so we pre-center with what we know, and then we do quick scan. It's like if we see the specimen on the right, then we move it again, scan it again, like in just a couple, like 5 minutes maybe, and we keep on doing like very quick scan and quick reconstruction and moving on, which in the end is very time consuming because you can spend like 2 hours just centering one specimen, but never, yeah, of course, yeah, it would be better if it would be faster, but so far it's been working relatively okay. But yeah, it's like just the time to see if it works is always a bit frustrating. So it depends of the quality of the quick scan or the.
Yeah, sorry if I may fill in. It depends on your research question as well, because a reconstructed slice is a 2D part
Yes.
of a 3D thing. So if your question is, I want to find a growth line, and you have oriented your sample correctly or the way you want it, you can see on a first reconstructed slice, you can see this growth line and the vascular canals that I show. But if you want to know the 3-dimensional distribution, then you need to segment them out in order to visualize them. So that can take a bit longer sometimes. Yeah.
I would like to sum up everything that was said in the paleontological session, because we have still a bit of time, like 20 minutes. So we achieved like very exciting results, it seems, on very iconic taxa and fossils. But it seems that we are still going through some difficulties, and that the improvement and the appearance, like the creation of a new beamline, BM18, will be very exciting in this field. And I think that would be nice if we could have like a small discussion on this aspect. For example, if I invite Lee, Denis and Vincent to tell us exactly like the limitation and what they would expect from their fossils or from their data. And Paul, maybe if you don't mind to answer like what the beamline could maybe help us to achieve with that would be really nice.
I think that one of the things that comes up here that we're all poignantly aware of is the human cost that's going to come with this increased data. And I'd like to touch on that just a little bit more. I don't think it's a viable future to think that we can take young people and have months and months and months doing reconstructions of these. You saw that, I mean, the scale of the data sets that I'm proposing are larger than anything that you were seeing there, and you see the investment that has to go in that. And so I think that the collaborative investment in machine learning, artificial intelligence, that can actually at least bring that project closer to usable data based on densities, based on the geochemistry and other aspects of this, have got to be the future that we have to invest heavily in, because I suspect, and Paul can correct me, but while the data quality goes up, the data size and the data complexity goes up. And spending the helpful lives of masters and PhD students is one thing, but we have to move to a place where the machines are taking that away from us.
So about machine learning, it's clear that it is one of the directions where we start to go, and in fact we already made tests also. We just made one test on a fossil so far that was on Alscaraptor, a small dinosaur that we scanned 2 years ago. And to be honest, I gave the data to my daughter that is 11 years old with remote connection to the computer from home to the ESRF. She was drawing on the screen for fun during 1 hour to say where the bones are and so on. Then I trained the computer with that. And the day after, I had the better segmentation than what we made with 4 scientists in 6 months. So I think clearly machine learning and deep learning is the way to go for the segmentation. It will not solve all the problem, because it works if the data are very good. If you have crappy data with a lot of artifacts and so on, you can train as much as you want, you will segment artifacts. So the quality of the data is always the start. So that's why we are pushing like, we make this project with BM18 and so on. The thing is, the first key is to make sure that you have the best possible quality, and then you can apply all these new technologies for machine learning and so on to really push to go faster, to be better for segmentation, and so on. So you have to see that as a continuum in many things. You need all the parts of the chain to be able to reach the result. So Sophie was asking a bit about the capacities for the BM18. So I will show some more details on Friday, but to do that very rapidly, the maximum size we had before was 50 centimeters by 16. With BM18, it will be 2.5 meters vertically, 1 meter horizontally, 300 kilograms, and able to cover without having to dismount anything. So you have all the detector can change themselves, the beamline can tune itself, so you do not need to dismount the sample and so on. You can cover from 200 microns for full scan to 0.7 microns for spots. And all that, you have continuous pixel size from 1 micron to 27. Then you have 50 microns, 100 microns, and we are planning a kind of super resolution detector that can cover the full field of view at 25 microns. But don't dream too much about something like that. It means 1 petabyte of data per day. So that's why we need the machine learning. It is the problem when you push on so many things and you make the beamline more automatic, you make more data, faster, better, but it means also that you will work on more difficult case. So at the end, even each time you gain on the technical thing, it does not mean that life will be easier. It just means that you will do things that are more difficult. So at the end, we will continue to develop. I mean, it's the only way to go.
Thank you very much. I have a question because you say so you will probably produce like peta of data. No, maybe not always, but quite a lot. So do we have like all the processing that will follow all the servers and everything at the ESRF? No, okay.
We have part of it. It's one part of the big development within the EBS. So there are completely new clusters. There are supercomputers based on GPU calculation and so on. And there are many people working on the automatic workflow for the tomography to make sure that first, very rapidly during the experiment, we have a feedback on what we are doing. So not only seeing one slice per scan, but seeing the complete scan very rapidly in a way that you can really select for the next one without having to dismount anything. But then when you want to go to the full quality, in this case, you need the full power for the calculation. So it's really huge infrastructure, and we need a lot of developments in the software aspects. So all that is ongoing. But I would say when you start to make the math for the amount of data, you also hit another problem that is data storage. I mean, being able to process rapidly is one thing. Being able to store all that is another problem, and it's a huge one. So one of the directions we took, I think 3 years ago, is to use in an early systematic way data compression. So it's a kind of against the religion in tomography. Normally, when you do tomography with Synchrotron, you do not want to do any destructive compression because you want to keep everything. In fact, after some time, you have to do it. So, and I would say many people were afraid of that, but we moved to JPEG 2000 format that can gain a factor 10 in terms of volume. And when you quantify the error, it's less than the natural noise of your detector. So it means you do not see it at all. So it's also part of the thing. To be able to deal with all that, you need also to play with compression and so on.
Just one quick comment was that just to give all of you hope, 11 years ago when we did the Sediba skull, it produced this astronomical data set of 15 terabytes. The total data was, we had 3 5-terabyte drives, right? Yeah. That's right. And so, and that just seemed so off the charts at that time, you know, and now your iPhone can sort of deal with that. So, or a little bit more than that, but a good iPhone could do it. But that, you know, we are catching up with that. So I don't think we should be afraid of the production of data, even if we do have to wait, but it'd be better to solve it now.
Yeah, if you scan an Archaeopteryx, they're typically quite dinosaurs in large limestone slabs. So this hierarchical aspect that you can zoom in is very important, because if you look at the anatomy of the animal, how the bones stick together, and then you want to look at microanatomy, what does the bone itself look like, and then microstructure, you need to zoom in on a specific place again. When we were doing the experiments, we were very careful, but sometimes we needed to remount the Archaeopteryx over and over again to get just the field, in the field of view that we were interested in. If you have an automated setup that allows you to switch resolutions on the fly, you do not need to handle the specimen as much, which makes it easier, life easier for you. You can even automate change scans overnight when you're not there or remotely controlling it. And that will help a lot. And also the fact that you know exactly which part you are scanning in each of the scans. So you don't need to manually superimpose these parts, but you can have a view in which you have the overview, clearly zoom in on this part, have the bone itself, and then have the microstructure. This is something that Vincent also touches on, because if you want to have this coherence, if you want to understand it all the way through, you can identify a feature in your larger scan and then zoom in on it without having to manipulate the specimen itself.
Yeah, and it has a second effect that is very important in terms of algorithmic reconstruction. As all the scales of the different scans are within a single 3D referential, it means that you can use the data from the low resolution scan to improve the quality of reconstruction for the high resolution one. And it's very important for local tomography, for instance, when you are scanning a very small volume in a large object. So we are able to do it now, but with a lot of artifacts due to this local tomography geometry. As soon as you go with real multi-resolution, you can correct for all these effects. So it's also, it's not only more convenient, it's also a way to have much better data.
I have another question, and it's related to what Denis presented, because he works on Archaeopteryx, which is a flat bone, fossil on a slab. So do you think that BM18 could also improve, because I know that you have some artifact working with flat fossils. Could BM18 be a solution as well?
Let's say it will not be the absolute solution, because when you are dealing with flat objects, you have missing data, whatever you do. So BM18 will be able to reach higher energy, meaning that you can go through more material. So you will have less missing angle, but you will still miss data. But also you will have better coherence, so better phase contrast. So you are still missing part, but finally what you miss is less than before. So the data will be better, but still will not be perfect along the axis of the plate. But we can also think with some workaround solution, and especially combining the tomography with other techniques such as scattering tomography. So we made some tests some years ago that can give you a bit of information for the third dimension, or even something much simpler that would be a surface scan in the same time that give you the external shape. Because if you can give to the reconstruction algorithm the external shape, you can correct for most of the artifacts that are linked to the missing angle. So many things will come from algorithmic processing, but as I said, it works only if you have good data from the beginning.
Thank you very much. Yes? You have a question?
Yeah. Maybe it's, again, as the X-ray scientist coming in, the more you go up in energy, the more Compton you're going to have, where basically, all the coherence is coming from Rayleigh scattering. And in the moment in which you increase the Compton contribution, that will basically gives you background and so on. Would that be a limiting factor at some point? Have you seen anything in this direction? Do you will need to have some kind of filtering in order to get rid of all the low energy X-rays that are coming out of your...
Yeah, in fact, the easiest way to deal with that is the size of BM18. When we will be at the highest energy, we will be with a detector 40 meters from the sample. And the scattering is going in nearly every direction. So just by the distance, you reduce a lot the scattering. And if it's not sufficient, there are also algorithmic corrections. So basically, you do the first scan of your samples, and you do a second scan where you have absorbing mask on the front of the detector, and like that you can make a low frequency reconstruction of the scattering contribution and remove it from the data. So yes, we have solutions, but in most of the cases, and it's what we already saw on ID19, just increasing the distance, first you have the phase contrast, that is what you want, and also you reduce the problem of scattering.
Thank you very much. I thank you all very much for this very interesting talk. Thank you, Paul, for all the answers. And Marin, it's to you.
Yeah, thank you all and to all of you.